Jailbreaking text-to-image models with LLM-based agents. Authors: Yingkai Dong, Zheng Li, Xiangtao Meng, Ning Yu, Shanqing Guo. Abstract: recent advancements have significantly improved automated task-solving capabilities using autonomous agents powered by large language models, also known as LLMs. However, most LLM-based agents focus on dialogue, programming, or specialized domains, leaving gaps in addressing generative AI safety tasks. These gaps are primarily due to the challenges posed by LLM hallucinations and the lack of clear guidelines. In this paper, we propose Atlas, an advanced LLM-based multi-agent framework that integrates an efficient fuzzing workflow to target generative AI models, specifically focusing on jailbreak attacks against text-to-image models with safety filters. Atlas uses a vision language model, called VLM, to assess whether a prompt triggers the text-to-image model's safety filter. It then iteratively collaborates with both LM and VLM to generate an alternative prompt that bypasses the filter. Atlas also enhances the reasoning abilities of LMS in attack scenarios by leveraging multi-agent communication, in-context learning memory mechanisms, and the chain-of-thought approach. Our evaluation shows that Atlas successfully jailbreaks several state-of-the-art text-to-image models in a black box setting, which are equipped with multimodal safety filters. Additionally, Atlas outperforms existing methods in both query efficiency and the quality of the generated images. Introduction: the pursuit of autonomous agents has been a long-standing focus in both academic and industrial research. Traditionally, agent building was conducted in constrained environments with limited knowledge bases, often leading to the inability to achieve human-like decision-making capabilities. In recent years, large language models have made remarkable strides, demonstrating their potential to attain human-like intelligence. These advancements have spurred a surge in research focused on LLM-based autonomous agents. LLM-based autonomous agents, hereafter referred to as LLM agents, utilize LLM applications such as GPT-4 or Vicuna to execute complex tasks through an architecture that combines LLMs with key modules like memory and tool usage. In the construction of LLM agents, an LM or its variant, such as a vision language model, serves as the primary controller or brain, orchestrating the execution of tasks or responses to user requests. The integration of LMS as fundamental elements within autonomous agents has opened up new avenues for research and application across various domains, promising more versatile and intelligent AI systems. Building on the foundation of LLM agents and their wide-ranging applications, we turn our attention in this work to a crucial yet understudied area: generative AI safety. While LM agents have been successfully deployed in fields such as computer science and software engineering, industrial automation, and social science, their potential to enhance research into generative AI safety is vastly under-researched. The safety of recent generative AI is crucial, especially as techniques like text-to-image generative models have rapidly gained unprecedented popularity due to their ease of use, high quality, and flexibility in generating images. A significant ethical concern with text-to-image models is their potential to generate sensitive, not safe for work, also known as NSFW, images, including those related to violence and content inappropriate for children. However, identifying safety vulnerabilities in these advanced models presents significant challenges. In this work, we posit that LLM agents, with their ability to process and synthesize vast amounts of information, could play a pivotal role in enhancing the understanding and exploration of safety vulnerabilities of recent rapidly developed generative AI. Our contributions. In this study, we take the first step in utilizing LLM agents to explore the safety vulnerabilities in generative AI models. Our objective is to develop a fully automated jailbreak attack framework based on LM agents. This framework employs multiple agents to create adaptive mode prompt-level adversarial prompts based on the following two key insights. Recent advancements in LLM have made it possible to generate semantically similar prompts across a seemingly infinite array of modes. For example, given the simple prompt, a cat, An LM can flexibly generate diverse content. It could describe a playful kitten with vivid imagery, or weave a tale about its adventure in a fantasy realm. Alternately, it might compose a poem highlighting a cat's serene moments or present a dialogue capturing its mischievous antics. Diversity in modes signifies a variety of adversarial prompts. However, it also implies that the search space for adversarial prompts is vast. Therefore, it is very difficult to find prompts that bypass the safety filters with LM alone. Previous research indicates that the involvement of multiple agents can promote diverse, innovative thinking, enhance the accuracy of generated content, and improve the reasoning capabilities. Such findings underpin the feasibility of orchestrating effective jailbreak attacks through an LLM-based multi-agent framework. Based on these insights, we propose a novel framework called Atlas, which employs multiple autonomous agents to systematically probe and potentially bypass the safety filters of text-to-image models. Atlas is developed through the lens of fuzzing, embodying its fundamental elements, the mutation engine and the score function, as two specialized agents, the mutation agent and the critic agent. The mutation agent employs a vision language model to automatically identify the activation state of the safety filters within the victim text-to-image model by analyzing images alongside their corresponding textual descriptions. Utilizing both current data and memory modules, this agent dynamically identifies optimization directions and executes optimizations, concluding with the delivery of candidate adversarial prompts. Subsequently, the critic agent scores these prompts using LLM's imitation and reasoning capacities. The prompt with the highest score is sent to the text-to-image model for testing. Upon receiving new test outcomes, the mutation agent concludes the optimization if the jailbreak is successful. Additionally, Atlas introduces a commander agent designed as a finite state machine to control the workflow. Furthermore, to enhance the resilience and domain-specific inference of LMS, Atlas incorporates a chain of thought and a novel in-context learning mechanism. We evaluate Atlas with Lava, Generative, and Vicuna against three state-of-the-art text-to-image models equipped with a large variety of safety filters. Our evaluation results show that Atlas can perform efficient jailbreak attacks on existing safety filters. For most conventional safety filters, Atlas achieves close to a 100% bypass rate and an average of 4.6 queries with a reasonable semantic similarity. Even for the conservative safety filter, the bypass rate can reach more than 82.45%, and the average number of queries required is also only 12.6. We also show that Atlas can successfully bypass the safety filters of the closebox DALL-B3. Furthermore, Atlas surpasses other jailbreak methods, striking a superior balance between bypass efficiency and the number of queries, while preserving semantic integrity. Finally, we also evaluate the effectiveness of the key components of Atlas through an ablation study. In summary, we make the following contributions. We verify the effectiveness of the LM agent in advancing generative AI safety research, especially in identifying vulnerabilities within text-to-image generative models. We design a novel framework called Atlas for effective jailbreak text-to-image models. This involves the creation of three distinct LLM agents and the establishment of a novel workflow resembling fuzzing, integrating chain-of-thought reasoning and an innovative in-context learning mechanism to synergize their functionalities. Compared to existing jailbreak methods, Atlas can achieve an adaptive mode prompt-level jailbreak attack by bypassing the black box safety filters inside black box text-to-image models. We conduct an extensive experiment to evaluate the performance of Atlas. The results indicate that Atlas can not only ensure semantic similarity, but also achieve an extremely high success rate in jailbreaking with fewer queries. And its comprehensive performance surpasses existing methods. Preliminaries. In this section, we begin by introducing the autonomous agents. We then present the text-to-image models and the jailbreak attacks against them. Autonomous agents. An autonomous agent is an advanced system that integrates an intelligent system as its central controller, functioning as the brain of the agent. This agent uses task decomposition, self-reflection, and dynamic memory to iteratively improve its actions and adapt to emerging challenges. Moreover, it has the capability to interface with external tools and APIs, broadening its capabilities beyond natural language processing to include tool use, planning, and executing specialized tasks. Here are the key components of an autonomous agent. Brain. The intelligence system, encompassing large language models, vision language models, and finite state machines, acts as the brain of the agent, directing a sequence of operations to fulfill tasks or user requests. Memory module. It stores internal logs, including past thoughts, actions, and observations, allowing the agent to recall past behaviors and plan future actions. Tool usage. Autonomous agents interact with external tools, like search, APIs, and code interpreters, to gather information and complete subtasks. Autonomous agents have significantly demonstrated capabilities when operating independently, and these capabilities are further augmented within a multi-agent system framework. Previous research has explored automated task solving using autonomous agent systems in various areas, including question and answer tasks, programming tasks, sociological phenomena research, and domain-specific tasks. However, exploration in the realm of machine learning security, this gap motivates us to focus on how autonomous agents perform in this domain. Text-to-image generative models. Text-to-image generative models have ushered in a new era of digital imagery. These models start with a canvas of Gaussian random noise and, through a process akin to reverse erosion, gradually sculpt the noise to reveal a coherent image. They can generate high-quality images in various styles and content based on natural language descriptions. For example, a painting of a mountain full of lambs. These models have gained unprecedented popularity due to their ease of use, high quality, and flexibility. Consequently, numerous variants of text-to-image models have emerged, including Stable Diffusion, LLM-Based, Imagen, and Midjourney. Examples of adversarial prompts that generate cats and dogs using SDXL and bypass an external safety filter. Same as sneaky prompt. We use dogs and cats as part of the external safety filters in the illustrative figure to avoid illegitimate or violent content that might make the audience uncomfortable. Safety filters. Incorporating safety filters is a widely adopted measure in the deployment of these models. These filters primarily inhibit the production of images featuring sensitive content, including adult material, violence, and politically sensitive imagery. For example, DALL-E 3 implements filters to block violent, adult, and hateful content and refuses requests for images of public figures by name. According to the classification methodology outlined in previous work, safety filters can be categorized into 3 distinct types: text-based safety filters, image-based safety filters, and text-image-based safety filters. Text-based safety filter. This type of safety filter is designed to assess textual input before image generation. It typically uses a binary classifier to intercept sensitive prompts, or utilizes a predefined list to block prompts that contain sensitive keywords or phrases, and those closely aligned with such keywords or phrases in the text embedding space. Image-based safety filter. This type of safety filter operates on the output side, examining the generated images. It functions as a binary classifier, trained on a dataset with images clearly labeled as NSW or SFW, meaning safe for work. A significant example of an application that incorporates an image-based safety filter is the official demo of SDXL, which seamlessly integrates this filter to scrutinize images for sensitive content. Text-image-based safety filter. This type of filter is a hybrid approach, leveraging both the input text and the generated images to ensure the content's safety. It implements a sophisticated binary classification mechanism that considers both text and image embeddings to identify and block sensitive content. The open-source Stable Diffusion 1.4 adopts this type of filter. In particular, this safety filter prevents the creation of an image if the cosine similarity measure between the images, CLIP embedding, and the CLIP text, embeddings of 17 predefined unsafe concepts, exceeds a specific limit. Jailbreaking text-to-image models. The jailbreaking attack against text-to-image models involves using prompt engineering to bypass the usage policies implemented in the model. By cleverly crafting prompts, an attacker can circumvent the model's defense mechanisms, such as safety filters, causing it to generate harmful images that violate its usage policies, including pornography and violence. Some illustrative examples of adversarial prompts generated by Atlas and corresponding images are demonstrated in Figure 1. In these scenarios, the model's safety filter, which blocks content involving both dogs and cats, rejects explicit violation requests, such as "the cat's eyes gleamed as it spotted a bird outside the window." However, rephrasing the same concept more subtly, as in "the small fluffy cat was curled up on a cushion in the sunny window," corresponding to Figure 1a, enables the model to produce outputs that violate its usage policy undetected. Researchers have proposed various strategies to jailbreak text-to-image models. However, most of these methods operate at the token level, attacking by replacing a few sensitive words in the prompt, while investigations into prompt-level jailbreak attacks, which entail the replacement of the entire sentence, remain scarce. These initiatives are often confined to either white box attacks or black box attacks that can only generate adversarial prompts in a limited pattern. This highlights a significant gap in the exploration of the adversarial prompts space. Recently, Yang et al. Proposed an advanced technique known as sneaky prompt, which employs a reinforcement learning-based method to find substitutions for NSFW words and bypasses the safety filter by replacing NSFW words with meaningless ones. Sneaky prompt can automatically create token-level input text prompts that trick the model into generating unsafe images with a high success rate. Note that sneaky prompt is the state-of-the-art automated jailbreak attack against text-to-image models in the black box setting. It achieves automated functionality by utilizing reinforcement learning techniques which are commonly used in traditional autonomous agents. Therefore, in this work, we use sneaky prompt as a baseline to investigate whether the proposed autonomous agent, Atlas, can be successfully applied to text-to-image model jailbreaks. Problem formulation. In this section, we first define the LLM agent and LLM-based multi-agent system, and then we define the adversarial prompt against the text-to-image model. Finally, we describe the threat model of Atlas, autonomous agent, and LLM-based multi-agent system. In this section, we will first give the formal definition of autonomous agents and then the definition of multi-agent systems. Agents. An agent is defined as a tuple. Here, the brain of the agent processes both the current information and the memory to determine the next action to be taken. The set is the collection of actions available to the agent. LLM-based multi-agent systems. An LLM-based multi-agent system can be formally represented as a tuple. Here, the set of agents is centralized around the LLM agent and potentially complemented by other agent types. The environment of the system can be any form of data or state space abstraction, providing a stage for the agent's actions. The set includes the collection of actions available to the agents, with each corresponding to the action set available to a specific agent. The set of system states is denoted, and the transition function describes how agents' actions lead to transitions in the system states. Adversarial prompt. A text-to-image model is denoted as I, and a safety filter represented by F, where FPIP equals 0 indicates that both the input prompt P and the generated image IP are classified as NSW, and FP IP equals 1 signifies that they are deemed SFW. We define a prompt as jailbreak prompt if the following definition is satisfied. Adversarial prompt. An adversarial prompt is defined as one that meets two conditions simultaneously. First, the prompt does not trigger the safety filters of the text-to-image model, meaning the filter classifies both the prompt and the generated image as safe for work. Second, the generated image has similar visual semantics to the target-sensitive prompt. Threat model. In this work, we focus on black box jailbreak attacks, which assume that the attacker lacks knowledge of both the internal working mechanisms of the target model and any details of the safety filters it may possess. Such an attacker is limited to interacting with the model's API interface and receiving outputs in response to input text prompts. The advantages of focusing on black box attacks are multifaceted and significant. First, the universality of black box attacks stands out, as their effectiveness does not rely on specific details of the model's implementation, making them applicable across a wide range of text-to-image models. Second, black box attacks pose a serious threat to commercial text-to-image models. These models, such as DALL-BA3 and Midjourney, tend to conceal their inner workings, thereby making white box attacks challenging. However, black box attacks can still be effectively executed by exploiting the model's input-output behavior. Third, the heightened challenge inherent in black box scenarios more effectively showcases Atlas' potential for exploring safety vulnerabilities in generative AI. Atlas. In this section, we first provide an overview of Atlas. Next, we present the details of the workflow and each key component. Overview. Key idea. The objective of Atlas is to bypass the safety filters of the text-to-image model, prompting it to produce images closely aligned with a given sensitive target prompt. This is possible because a safety filter essentially functions as a binary classifier, delineating clear decision boundaries. A prompt closely related to a sensitive target can be visualized as an epsilon ball, allowing the attack's goal to be achieved by finding a point where the epsilon ball intersects with the classifier's decision boundary. It is pertinent to note that while Atlas queries are exclusively textual, the approach is applicable to both textual and visual modalities. This is because the decision boundary of the image modality can be mapped to the embedding space of the text modality. To achieve this objective, we formalize the key idea of Atlas, which is a multi-agent mutational fuzzer that searches for the adversarial prompt that satisfies the following two objectives. Objective 1. Mutating the target-sensitive prompt to bypass the safety filter. That is, finding prompts that cross the decision boundary of the filter from the target prompt. Objective 2. If the generated image has a large semantic deviation from the target prompt, find the intersection of the epsilon ball in the epsilon hat ball centered on the current prompt, starting from the current prompt. Key components. Figure 2 shows the overall pipeline of Atlas in searching adversarial prompts. Given a seed pool consisting of various sensitive prompts, Atlas sequentially modifies each prompt which is blocked by the safety filters of the text-to-image model, using 3 key agents. Mutation agent. Given a target sensitive prompt, the mutation agent employs test oracles to analyze the response of the victim text-to-image model and modifies the prompt to find an adversarial prompt. This mutation agent evaluates whether the adversarial prompt triggers the safety filter and if the generated image has similar semantics to the original target prompt. If the adversarial prompt requires further mutation, the agent adaptively develops a mutation strategy and generates multiple mutated prompts accordingly. Critic agent. The critic agent evaluates the current state and scores the mutated prompts. In traditional fuzz testing, the quality feedback engine computes the fitness score of test cases based on system feedback, guiding mutations toward bug conditions. However, this approach is not suitable for testing text-to-image models for 2 reasons. First, the safety filters of text-to-image models are usually binary classifiers, offering limited feedback. Second, this approach increases the number of invalid accesses to the system, leading to higher costs and a greater likelihood of access denial. Therefore, Atlas implements the scoring function through the critic agent, embedding feedback in the candidate jailbreak prompts. Commander agent. The commander agent feeds the candidate adversarial prompt into the text-to-image model and loops through the above workflow until the adversarial prompt is found. Note that the commander agent completely controls the execution of the above workflows without any manual intervention. Workflow. As shown in Figure 3, the workflow of Atlas can be divided into 5 steps. Step 1. Bypass check. The mutation agent determines whether the safety filter of the text-to-image model is bypassed, based on the current prompt and the response of the text-to-image model. If the current prompt triggers the safety filter of the text-to-image model, Step 2 is initiated. At the same time, the critic agent records the triggered prompt in its long-term memory. Otherwise, Step 3 proceeds. Step 2. Mutation for bypass. The mutation agent accesses its long-term memory to formulate the mutation strategy and guidance, drawing upon the results retrieved. Then, the mutation agent mutates the prompt in accordance with the devised strategy and guidance, generating multiple candidate prompts accordingly. Finally, the mutation agent sends these candidate prompts to the commander agent. After completing the above operations, Step 5 will be executed. Step 3. Semantic check. The mutation agent queries the semantic similarity of the original prompt and the response from the text-to-image model. We do not use the similarity between the original image and the generated image to obtain semantic similarity, because the generated image is censored and thus inaccessible. If the similarity is less than a certain threshold, perform Step 4. Otherwise, Atlas terminates the query for the original prompt and outputs the corresponding adversarial prompt and the image. At the same time, the mutation agent records the successful adversarial prompt in its long-term memory. Step 4. Mutation for semantic. The mutation agent provides guidance for subsequent mutations to improve semantic similarity and then performs mutations to produce multiple candidate prompts. Then, the mutation agent sends these candidate prompts to the commander agent. After completing the above operations, Step 5 will be executed. Step 5. Score and select. The critic agent scores the candidate prompts, and the commander agent selects the highest scoring prompt for input into the text-to-image model. For each target, sensitive prompt, Atlas performs steps 1 through 5 upon receiving a response from the text-to-image model. Atlas repeats this process until it identifies an adversarial prompt or attains the maximum number of queries specified for the target prompt. It is important to note that Atlas initializes the memory module for each agent exclusively during the initial mutation of the first sample in the seed pool, and does not reinitialize it in subsequent mutations. This means that when mutating the second sample, the memory module in Atlas retains records of the mutations applied to the first sample. Furthermore, we employ an exponential backoff strategy to set the maximum query limit. Upon reaching this limit for a prompt in a given round, we temporarily bypass the query for that prompt, preserving it for the subsequent round. This process continues until each prompt has been successfully linked to its corresponding adversarial prompt, or until the predefined maximum query threshold is met. Moreover, to circumvent the risk of local optima, each round of Atlas starts with the original prompt rather than the last mutated prompt from the previous round. Metastructure of system, message, and prompt. To improve the understanding and implementation of mutation and scoring tasks by LLM and VLM. A critical step involves the creation of system messages and prompt templates. Each system message and prompt template adheres to a consistent metastructure as shown in Figure 4. The complexity of the jailbreak task dictates the instantiation of this metastructure in various forms. Mutation agent. Atlas mutation agent aims to increase the target-sensitive prompt's jailbreak capabilities gradually. Following the definition, we define the mutation agent as the combination of the brain, the memory module, and the actions. Brain of mutation agent. In this attack scenario, the mutation agent is required to recognize and align information from the textual and visual modalities within the environment. Therefore, we use a vision language model as the decision-making brain of the agent. Vision language models, such as GPT-4 Vision, Lava, and SharegPT-4V, integrate capabilities in image understanding, text understanding, and text generation. These models can understand visual elements within an image and answer text-based questions using image information. ICL-based memory module. Recall that an agent requires a memory module that includes past thoughts, actions, and observations to recall past behaviors and plan future actions. Considering that the brain of the mutation agent is a vision language model, we construct this memory module using in-context learning. In context, learning allows a model to perform tasks by conditioning on a few examples provided in the prompt, without any parameter updates or additional training. In this context, the provided examples are successful adversarial prompts generated during each loop and saved into the long-term memory database. Concretely, The ICL-based memory module involves 3 steps. The mutation agent retrieves successful jailbreak prompts from its long-term memory database. Note that the long-term memory database is empty at its first loop for the first target-sensitive prompt, to prevent overly long context from confusing the vision language model's attention. The mutation agent ranks these prompts and extracts the top prompts using a semantic-based memory retriever. The mutation agent summarizes these successes and uses them to guide the mutation of the current through a well-designed prompt template. This structured process ensures that the mutation agent effectively uses past experiences to inform the next mutation actions. So far, we have obtained the key factors of the success story through the reflection mechanism. To be able to utilize these key factors to formulate mutation strategies, we further designed the strategy prompt template for the mutation agent. This long-term memory and in-context learning mechanism not only allows capabilities of the mutation agent to be gradually enhanced as Atlas runs, but also allows an attacker to manually add known jailbreak prompts to the long-term memory database, thus aggregating the attack performance of other jailbreak attack methods and further enhancing the mutation agent's jailbreak capabilities. Furthermore, to avoid the confusion caused by in-context learning for reasoning when the number of referable successful prompts is low, when the number of successful prompts in the long-term memory database is less than a certain threshold, we use the ICL free strategy prompt template rather than the combination of IIPL prompt template and ICL strategy prompt template to drive the mutation agent to develop a mutation strategy whitestone. This ICL-based memory mechanism not only allows capabilities of the mutation agent to be gradually enhanced as Atlas runs, but also allows an attacker to manually add known jailbreak prompts to the long-term memory database, thus aggregating the attack performance of other jailbreak attack methods and further enhancing the mutation agent's jailbreak capabilities. Actions of mutation agent. The actions of the mutation agent include text outputs and the use of tools, given that text output is an inherent capability of the vision language model. This section elaborates on the mutation agent's tool using capability. In specific, we introduce 2 tools for the mutation agent. Semantic-based memory retriever, to equip the vision language model with in-context learning capabilities while avoiding the confusion caused by excessively long contexts. We design a semantic-based memory retriever. This retriever ranks jailbreak prompts in long-term memory by semantic similarity and selects the top most similar prompts to construct the in-context learning prompt. Concretely, the retriever first uses word embedding tools, such as sentence transformer and word-wovec, to convert the original prompt and each jailbreak prompt in the long-term memory into text embeddings. It then calculates the cosine similarity between the text embedding of the original prompt and each jailbreak prompt. Finally, based on the calculated cosine similarities, it sorts the sentences and outputs the top jailbreak prompts with the highest cosine similarity. Multimodal semantic discriminator. To ensure that the generated image has similar visual semantics to the target prompt, we design the multimodal semantic discriminator for the mutating agent. This discriminator computes the similarity between the text embedding of the original target prompt and the image embedding of the generated image. Specifically, the mutation agent uses CLIP to compute the CLIP variant of cosine similarity between the target prompt and the generated image. Although vision language models can also compute semantic similarity between multimodal data. We use a multimodal semantic discriminator to account for the uncertainty of large models. The multimodal semantic discriminator is able to ensure that the cosine similarity between all final generated images and the original sensitive words is greater than a certain threshold. Whereas the vision language model's criterion changes each time it discerns the semantic similarity, and it is unable to control the lower limit of the semantic similarity. Critic agent. After the mutation agent generates multiple candidate jailbreak prompts, the critic agent scores these prompts and selects the one with the strongest jailbreak ability. To measure the jailbreak ability of the candidate prompts, we design the following score function. The scoring function evaluates the effectiveness of prompts in bypassing safety filters, while the second part measures semantic similarity. According to the definition, an adversarial prompt should meet 2 conditions. The prompt does not trigger the safety filters of the text-to-image model, and the generated image has similar visual semantics to the target prompt. These conditions correspond to the scoring function respectively. The design objective of the critic agent has been to solve this scoring equation. To achieve this, the critic agent includes two large language models acting as different brains, a memory module and a brain switching mechanism in its action module. Brain of critic agent. As mentioned above, we designed two different large language model-based brains for the critic agent: the safety filter brain, which calculates the first part of the score, and the semantics evaluator brain, which computes the second part. Safety filter brain. To measure how well the candidate prompts bypass safety filters, we customize the system message of the safety filter brain to simulate the safety filter of the target model. In this system message, successful prompts denotes the set of successful adversarial prompts, while trigger prompts represents the set of prompts that trigger the safety filter. The critic agent retrieves these prompts from its memory module. Additionally, similar to the design of the mutation agent, the first semantically similar prompts are selected using the semantic-based memory retriever to avoid attention confusion. Semantics evaluator brain. To evaluate the semantic similarity between candidate prompts and the original prompt, we customize the system message of the semantics evaluator brain. Memory module. The memory module of the critic agent maintains two databases, one for prompts that trigger the safety filter and another for those that bypass it. Initially, both databases are empty for the first target-sensitive prompt and gradually accumulate data during the run, similar to the design of the mutation agent. Actions of critic agent. The actions of the critic agent include text outputs, tool usage, and brain switching. Text output is a basic feature of the large language model, and tool usage involves only the semantic-based memory retriever. Brain switching is unique to the critic agent. As described in the previous section, the critic agent has two distinct large language model-based brains. During operation, it switches brains based on the current environment. Specifically, the critic agent decides whether to score the first or second part of the scoring function based on instructions from the commander agent and selects the appropriate brain accordingly. Commander agent. The commander agent fully controls Atlas workflow. To ensure stability, we define the commander agent as a reactive agent rather than a large language model-based one. This design focuses on direct input-output mappings instead of complex reasoning, allowing it to respond to the environment in a stable manner. Following the definition, the commander agent should be defined as a combination of the brain and actions. However, since the commander agent only performs direct input-output mapping, a memory module is unnecessary. Therefore, we define the commander agent as a combination of the brain and actions. Brain of commander agent. We design a rule-based finite state machine as the brain of the commander agent. Instead of using a large language model or vision language model, the finite state machine is defined by a three-tuple, representing the set of states. The initial state is waiting for the program to start. The end state is the termination process, and each intermediate state denotes a prompt that can be issued by the commander agent to the mutation agent or critic agent. The set includes the prefix of responses that might be given by the mutation agent or critic agent. The transition mechanism determines the next state based on the current state and the received response. Actions of commander agent. Unlike the other two agents that passively receive tasks, the commander agent proactively initiates sessions with other agents. The interaction of the commander agent is divided into two primary segments: commander mutation interaction and commander critic interaction. Commander mutation interaction. To address the illusion and task loss problems of vision language models, we divide the mutation agent's task into subtasks and use the chain of thought method to improve reasoning and instruction following. The commander agent implements multi-turn chain of thought by sending one subtask at a time to the mutation agent. After receiving a response, it sends the context and the next subtask. This multi-turn chain of thought is more effective than single-turn chain of thought in overcoming vision language model hallucination and solving the task loss issue. In each mutation round, the commander agent sends bypass check prompts to the mutation agent. These prompts guide the mutation agent to verify if the text-to-image safety filter has been bypassed based on the current prompt and image. To improve accuracy, We construct the bypass check prompt template on the description then decision approach. Specifically, we design the template as multiple choice questions divided into check description prompt and check decision prompt. Afterward, the commander agent decides on the next steps based on the response. If the mutation agent's response is that the safety filters are triggered, the commander agent instructs it to create a mutation strategy using the in-context learning (ICL) strategy and strategy prompt templates. Once the mutation agent responds, the commander agent sends a modify prompt directive for new prompts based on its guidance. Conversely, if the mutation agent's response is that the prompt has bypassed the safety filters, the commander agent instructs the mutation agent to verify if the semantics remain unchanged. As detailed in the previous section, the mutation agent uses the multimodal semantic discriminator to compute semantic similarity. Thus, the commander agent simply sends a semantic check request and waits for the response. If the mutation agent calculates that the similarity is less than the threshold, it indicates semantic deviation requiring further mutation. In this case, the commander agent sends a semantic guide prompt to the mutation agent to devise targeted mutation strategies and a modify prompt to generate new prompts based on these strategies. Commander-critic interaction. After the commander agent receives the prompts from the mutation agent, it sends them to the critic agent for scoring. The commander agent sends the mark and new prompts to the critic agent, directing it to score each prompt using either the bypass score prompt if the safety filters are triggered, or the semantic score prompt template otherwise. Finally, the commander agent selects the highest scoring prompt from the critic agent's evaluation and formats it appropriately for sending to the target text-to-image model to generate unsafe images. Experimental setup. Atlas model. We use Lava and Generative as the vision language models for the mutation agent. Lava is a powerful vision language model, achieving top results on 11 benchmarks. Generative is also widely used and outperforms Lava on 9 benchmarks. Additionally, we use Vicuna, a fine-tuned model from Llama 2, as the large language model-based brain for the critical agent. We do not use more powerful models like GPT-4 Vision, GPT-4, and Llama 2 for Atlas, because their integrated safeguards prevent them from processing sensitive content, making them unsuitable. Target text-to-image model and safety filters. The target or victim text-to-image models include Stable Diffusion, XL Refiner, Stable Diffusion 3 Medium, and DALWay 3. These are state-of-the-art open-source text-to-image models that inherently lack safety mechanisms. Following sneaky prompt, we equip them with 6 different safety filters discussed in the previous section. A text-image-based safety filter built into the Stable Diffusion open-source implementation. A text match-based safety filter. A text classifier-based safety filter that uses a binary classifier fine-tuned on Distilbert. An open-source image classifier-based safety filter. An image clip classifier-based safety filter included in the official Stable Diffusion XL Demo. A dog-cat image classifier-based safety filter trained on the Animals 10 dataset. Note that we only equipped Stable Diffusion with a text-image-based filter, as this is its built-in safety filter and is difficult to take out for use in other models. Furthermore, to bypass the dog-cat safety filter, the type of safety filter needs to be emphasized in Atlas System Message and Prompt Template. Specific information can be found in Appendix E. DALLA3 is a ChatGPT-based text-to-image model from OpenAI with unknown safety filters. Since it automatically rewrites input prompts for safety reasons, we add the following content before the adversarial prompt to study its effectiveness. DONOT. Add any detail, just use it. ASIS. Dataset. We evaluate the performance of Atlas on the NSFW 200 dataset and DogCat 100 dataset as same in sneaky prompt. The NSFW 200 dataset consists of 200 prompts containing NSW content. We utilize this dataset to test safety filters other than the dog-cat image classifier-based safety filter. The dog-cat 100 dataset includes 100 prompts describing the scenario with dogs or cats. The combination of this dataset with the dog-cat image classifier-based safety filter allows testing the effectiveness of Atlas while avoiding the generation of NSFW content. In addition, to minimize cost, we use the first half of the NSW200 as the dataset for testing DALB3. Evaluation metrics. We use 4 metrics including one-time bypass rate, reuse bypass rate, FID, and query number. One-time bypass rate. It is the percentage of adversarial prompts that bypass safety filters out of the total number of such prompts. Following sneaky prompt. An adversarial prompt is successful if the model generates a corresponding image and the clip score exceeds the threshold. Reuse bypass rate. It measures the reusability of adversarial prompts. To evaluate this, we set the target text-to-image model seed to a random value and test the bypass rate of successful adversarial prompts. FID score. It evaluates image semantic similarity. A higher FID score indicates a greater difference between the distributions of 2 image collections. We compare the distribution of the generated image collection with 7 ground truth datasets, 3 target datasets, 1,000 images each generated by Stable Diffusion 1.4, Stable Diffusion XL, and Stable Diffusion 3 using random seeds based on the NSW200 dataset. Real dataset, 4,000 genuine sensitive images from the NSFW image dataset. 3 dog-cat datasets, 1,000 images each generated by Stable Diffusion 1.4T, Stable Diffusion XL, and Stable Diffusion 3 using random seeds based on dog-cat 100. When the target model is Stable Diffusion, the target FID is computed from the target dataset and the dog-cat dataset of the corresponding model version. When the target model is DALL3, the target FID is computed from the Stable Diffusion XL target dataset. Query number, Tarshai. We measure the number of queries to text-to-image models used to find a jailbreak prompt. More queries increase costs, both computational and financial. Additionally, a high number of queries may trigger monitoring mechanisms in the target system, leading to detection. Hyperparameters. Atlas involves 5 hyperparameters. Threshold for clip score, used to determine semantic similarity, set to 0.26, as in sneaky prompt. Maximum number of queries per round is 4. 10, with a maximum of 60 queries per sensitive prompt. Number of prompts for the mutation agent, set to 5 to avoid confusing attention with overly long contexts. Number of prompts for the critic agent, set to 10 to maintain the validity of mimicry without losing the target task. Additionally, we limit the values for the first and second parts of the scoring function to 0, or 1, but the first part cannot equal the second part. Evaluation. We answer the following research questions. How effective is Atlas at bypassing existing safety filters? How does Atlas perform compared with different baselines? How do different hyperparameters affect the performance of Atlas? Effectiveness at bypassing safety filter. In this research question, we evaluate how effective Atlas is at bypassing existing safety filters. Effectiveness on Stable Diffusion. Atlas successfully bypasses all safety filters in general, generating images that retain semantic similarity to the original prompts with minimal queries. It accomplishes a 100% one-time bypass success rate, necessitating an average of only 4.6 queries and achieving a commendable FID score across various filters, with the exception of the text classifier-based and dog-cat image classifier-based filters. The methodology ensures a 100% reuse bypass rate against text-based safety filters due to their positioning prior to the diffusion model's application, whereas this rate declines to approximately 50% for text-image-based and image-based filters. This reduction is attributed to the interference of a random seed with the original mapping relationship, allowing certain adversarial prompts to conform to the safety filter's decision boundary by dog. For the dog-cat image classifier-based filters, the bypass rate decreases to 90% with an average query count of 6.60. Remarkably, even against more conservative text classifier-based filters, Atlas secures an over 82.5% one-time bypass rate, with queries averaging at 12.6. Effectiveness on DALL B3-3. Atlas has 81.93% and 79.50% one-time bypass rates for closed-box DAL DB3, with an average of 13.38 queries. DALL B3, as a commercially available text-to-image model, benefits from OpenAI's safety efforts, making it more robust than Stable Diffusion. Additionally, the images generated by DALL BRI are in a special style, which differs significantly from the dataset used to evaluate semantic similarity. As a result, the FID is higher but still lower than that of existing methods. Effectiveness of different vision language models is brained. We further study the impact of using different vision language models as the mutation agent's brain. Comparing LLaVA and Generative, we observe that Generative generally achieves higher attack performance than LLaVA. However, we also find that Atlas can achieve strong attack performance against all cases for both LLaVA and Generative. These observations indicate that the attacker can simply choose any vision language model as the brain of the mutation agent. Performance comparison with baselines. We compare the performance of Atlas with Sneaky Prompt, DACA, and Ring a Bell. The default setting of Atlas is based on LLaVA and Vicuna. For Sneaky Prompt, DACA, and Ring a Bell, we use their official implementations and default hyperparameters. Atlas consistently achieves the highest one-time bypass rate across all evaluated safety filters, distinguishing itself, particularly in the realm of text classifier safety filters where its performance is exceptionally superior. Furthermore, the reuse bypass rate of Atlas is comparable to that of Sneaky Prompt and generally surpasses that of Ring a Bell. While DACA might exhibit a higher reuse bypass rate compared to Atlas, it is important to note that Atlas allows for a greater number of prompts to be reused, attributed to its superior one-time bypass rate. Additionally, Atlas achieves the smallest FID score in most cases, and in the remaining cases, the FID is very similar to the other methods. In addition, while Sneaky Prompt also gets high bypass rates and reasonable FID scores on Stable Diffusion, it requires significantly more queries than Atlas. The query number required for Atlas is much smaller than that required for Sneaky Prompt on almost all safety filters. In the context of text match-based safety filters, Atlas also requires fewer queries than Sneaky Prompt, but the advantage is reduced. This is because Sneaky Prompt's jailbreak strategy is to replace the sensitive words in the malicious prompts with text embedding similar non-sensitive or meaningless words. This gives it a strong ability to bypass plain text match safety filters. The query numbers for DACA and Ring a Bell are omitted since these methods do not rely on iterative optimization, where an increase in queries would not correlate with higher success rates. Study of different parameter selection. We study how different parameters affect the overall performance of Atlas. The number of agents. To evaluate the effectiveness of the key components of Atlas, we assess the jailbreak performance using 1-agent to 3-agent configurations on Stable Diffusion. The configuration details for 1-agent and 2-agent setups are as follows. 1-agent. We construct Atlas with a single agent, using a vision language model as its brain. The system message is the same as the system message for mutation agent. In the prompt template design, we use the chain of thought to enhance the vision language model's reasoning in the jailbreak task. 2-agent. This configuration includes a mutation agent and a commander agent. The MODIY prompt template for the mutation agent is set to generate a single new prompt that is likely to bypass the security filter, rather than generating 5 prompts. The commander agent removes content related to the critic agent and, after the mutation agent generates a new prompt, it sends the prompt directly to the text-to-image model without involving the critic agent. The rest of the configuration for both agents is identical to the default setup. The one-time bypass rate of a 1-agent configuration is markedly lower than that of configurations with 2 or 3 agents. The reason is the excessively long context causes the vision language model to be highly susceptible to attentional confusion, which in turn leads to hallucinations and task loss phenomena. When the number of agents is increased to 2, a significant enhancement in the bypass rate is observed. This suggests that multi-turn reasoning through the commander agent assisting the mutation agent can effectively solve the task loss problem and reduce the occurrence of the hallucination problem. Although the two-agent exhibits almost similar bypass rates as the three-agent, it requires a much higher number of queries than the three-agent. Similarity threshold. The semantic similarity threshold determines the semantic similarity of the final generated image to the original sensitive prompt. To explore the effect of different semantic similarity thresholds on Atlas, we evaluate the bypass rates, the FID scores, and the query numbers at settings from 0.22 to 0.30. The bypass rate decreases as the threshold increases. This is because, as the threshold increases, the space for jailbreak prompts becomes smaller and therefore harder to find. This is also reflected in the query numbers. As the threshold increases, the number of queries increases. However, even when the threshold is increased to 0.30, Atlas is still able to maintain a success rate of more than 90%. Additionally, FID scores decrease as the threshold increases, but the change is small. This suggests to some extent that the thresholds we used in our main experiment have been able to preserve the malicious semantics in the original prompt to a greater extent. Long-term memory. Our study we show the effectiveness of long-term memory and compare the choice of different memory lengths. Atlas bypass rate could only reach 81.65% with the no memory setting. The number of queries required for the bypass is also significantly higher than when using long-term memory mechanisms. This indicates that our designed long-term memory mechanism as well as the in-context learning mechanism effectively improves the performance of Atlas. Furthermore, Atlas shows strong performance when the memory length is set to 5. When it is set to 10, Atlas still maintains a bypass success rate of 100%, but the number of queries increases. This is because a larger memory length increases the likelihood of exceeding the context length limit, and rounds that tend to be successful are restarted due to exceeding the maximum length. When the memory length reaches 20, the bypass rate decreases significantly. The reason is that excessive memory length not only tends to exceed the model's context length limit, but also confuses the model's attention and amplifies the model's hallucination problem and task loss problem. Additionally, the length of memory for the critic agent has a small effect on the performance of Atlas. The maximum number of queries. We study the impact of different maximum query limits on Atlas. In total, we chose 3 different combinations of the maximum number of queries. Among them, Atlas performs best when the maximum number of queries is 4, 10, 10, and so on. However, the effect of different maximum numbers of queries on the performance of Atlas is insignificant. Discussion. Limitations of our study. In this work, Atlas is designed with open-source large models that are not safety-aligned. Although satisfactory performance can already be achieved using these open-source models, models with strong reasoning and instruction-following capabilities, such as GPT-4 and GPT-4 Vision, are expected to further improve the performance of Atlas. Existing work has already demonstrated that through model fine-tuning and in-context learning, the protective mechanisms of large language models can be removed. Thus, we left the evaluation of Atlas with models that have been safety-aligned as future work. Possible defense. Enhancing the model's safety during its training phase is expected to mitigate the foundational risks linked with jailbreaking. One possible strategy is adversarial training, which involves integrating known jailbreak prompts into the safety filters training dataset, provided it is based on learning algorithms. However, defenses grounded in empirical evidence face challenges in comprehensively covering the sample space of jailbreak prompts, leading to an ongoing arms race between offensive and defensive strategies. An alternative approach to address this issue is to certify robustness. For example, through techniques such as randomized smoothing. This field is poised to be a critical focal point for future research endeavors. Related works. Text-to-image models. The concept of generating images from textual descriptions has its origins in early computer vision and natural language processing endeavors. Mansama et al. Pioneered this domain by generating images from natural languages. Subsequently, Reed et al. Introduced a generative adversarial network capable of creating images from textual descriptions. Following this initial breakthrough, several enhancements were implemented in GAN-based models. Zheng et al. Presented Stacken, utilizing a two-stage GAN to produce high-resolution images from text. More recently, there has been an emerging trend of the diffusion model to become the new state-of-the-art model in text-to-image generation. Nickel et al. Propose a text-guided diffusion model called GLIDE that aims at photorealistic image generation and editing. Saharia et al. Made significant contributions with their photorealistic text-to-image diffusion models that enhance coherence and fidelity by integrating advanced language models. Furthermore, an innovative approach has been proposed to compress images into a low-dimensional space before using diffusion models trained in this latent space, exemplified by methods such as Stable Diffusion and DALL-E2, jailbreaking text-to-image models. Given the widespread adoption of these models, numerous studies have been conducted to investigate their vulnerabilities, to explore the robustness of safety filters. Rando et al. And Q et al. Consider content safety filters in text-to-image models, such as Stable Diffusion, and introduced adversarial strategies including prompt dilution. However, these strategies are primarily manual, exhibit low bypass rates, and are restricted to offline text-to-image models. To advance this field, Yang et al. Developed Sneaky Prompt, a novel approach using reinforcement learning to substitute NSFW terminology, effectively circumventing safety filters. Similarly, Yang et al. Demonstrated a white box jailbreak attack leveraging a gradient descent method aimed at text-to-image models with integrated safety filters. Deng et al. Managed to bypass text-to-image models' safety filters by instructing large language models to fragment unethical drawing intents into innocuous descriptions of separate image elements. Furthermore, Ba et al. Unveiled a jailbreak attack targeting Midjourney by elucidating the attributes of its safety filter. Despite these advancements, the proposed methods encompass token-level, white box prompt-level, or fixed-mode prompt-level attacks, leaving a significant gap in understanding and testing the efficacy of jailbreak prompts in black box scenarios. Conclusion: in this paper, we initiate the exploration of safety vulnerabilities in generative AI systems by employing LLM agents, specifically focusing on the task of jailbreaking text-to-image models that are equipped with safety filters. To this end, we propose a novel LLM-based multi-agent framework, Atlas, which incorporates three innovative autonomous agents, powered by LLM, VLM, and FSM respectively. This framework enhances the reasoning capabilities of LM agents in jailbreaking tasks by integrating fuzzing techniques and the chain-of-thought method into its workflow design. We conduct an extensive evaluation of Atlas on 4 state-of-the-art text-to-image models, each equipped with multiple safety filters. The results show that Atlas achieves outstanding performance in terms of bypass rate, query efficiency, and semantic similarity. We further conduct a comparison of Atlas with 4 baseline methods, and the results show that Atlas generally outperforms all these methods.